Here's a game where you can remove any perfect square of stones. Sounds simple, right? But there's a catch. You don't need to find the move that gives you the most stones. You need to find a move that leaves your opponent in a losing position. And that tiny change in perspective is the entire trick behind Leetcode 1510. Today, we'll turn this game into a simple dynamic programming pattern you can reuse in other game theory problems. Problem breakdown. We start with n stones. Alice moves first. On every turn, a player can remove 1, 4, 9, 16, 25. In other words, 1 power 2, 2 power 2, 3 power 2, for power 2. The player who cannot make a move loses. So the question is, can Alice force a win if both players play optimally? Start with the smallest cases. Let's build some intuition. N equal to 1. Alice can remove 1. 1 to 0. Bob has no move. So, DP 1 equal to true. Alice wins. N equal to 2. The only square we can remove is 1. 2 to 1. Now Bob removes 1. 1 to 0. Alice loses. So, DP 2 equal to false. N equal to 3. Again, Alice can only remove 1. 3 to 2. And we already know 2 is a losing position. So Alice can force Bob into that losing state. Therefore, DP 3 equal to true. The key pattern. Now pause here. What did we just do? For n equal to 3, Alice didn't ask, what's the best square to remove? She asked, can I make the remaining state losing for my opponent? That's the game theory pattern. A state is winning if there exists at least one move that sends the opponent to a losing state. And a state is losing if every possible move sends the opponent to a winning state. In other words, win to there exists a move to lose. Lose to every move goes to win. This is the core insight. Define the DP. Let's define DPI as true if the player whose turn it is can force a win with I stones remaining. So, DP0 equal false. Why? Because if there are 0 stones, you can't make a move. Python code. Class solution. Def winner square game. Self. N. Int. Dash. Bool. DP equal to byte array. N plus 1. Squares equal to x equal to 1. While x into x less than or equal to n. Squares that append x into x. X plus equal to 1. For I in range 1, n plus 1. For SQ in squares. If SQ greater than I, break. If DP, I minus SQ, equal to 0, DP equal to 1, break. Return bool, DP n. Code walkthrough. Let's break down the important parts. DP equal to byte array, n plus 1. DP equal to byte array, n plus 1. Every state starts as 0. We use 0 to losing, 1 to winning. Byte array is also memory efficient because we only need one bit-like state conceptually, winning or losing. Generate squares, while x into x less than or equal to n. Squares that append x into x, x plus equal to 1. We generate every square that could possibly be removed. Process every state. For I in range 1, n plus 1. We're solving the game from smaller states toward larger states. That's bottom-up DP. Try every legal move. For SQ in squares. If SQ greater than I, break. If the square is larger than our current number of stones, we can't use it. Because the squares are sorted, we can immediately stop. The critical line. If DP, I minus SQ, equal to 0. This means, after my move, my opponent is in a losing position. And that's exactly what we want. So, DP equal to 1. Break. Once we find one winning move, we don't need to check anything else. Complexity. How many DP states? And for each state, we may try up to square root n. Perfect squares. Therefore, time complexity, O of n square root n. Space complexity, O of n. For n less than or equal to 100,000. This is efficient enough. Why this is a powerful pattern? This problem teaches an extremely reusable game theory DP pattern. Whenever you have 2 players, alternating turns, optimal play, a state that changes after each move. One player wins when the other reaches a losing state. Think, can I move my opponent into a losing state? Then your recurrence often becomes DP state equal to any, not DP, next underscore state. That's the important pattern. Interview insight. If an interviewer asks, why don't you simply choose the largest square? Your answer should be, because this is not a greedy optimization problem. The value of a move depends on the game state it leaves for the opponent. We need to know whether at least one legal move reaches a losing state. That's a much stronger interview explanation than simply saying, I used DP. You are explaining why DP is necessary. So the trick in Stone Game 4 isn't memorizing a formula. It's recognizing this pattern. Winning state to move to a losing state. Losing state to every move leads to a winning state. Once you start thinking in terms of winning and losing states, a whole family of game problems becomes much easier to attack. And that is the real skill this problem is testing.